Welcome friends in the video lecture series for diploma second year students. Our subject is applied mechanics and today we are going to discuss the work, power and energy. Myself is P.V. Raijada. I am working as a head of applied mechanics department at Government Polytechnic, Rajkot. So let us go to the topic and start the PPT. It is our unit number 6. In this first lecture we will discuss about work, power and energy. First of all, let us see the syllabus about applied mechanics subject. You can see the sixth topic, work, power and energy, is allocated 4 lectures in which total marks is given 10, out of which 2 are remembrance, 2 are understanding and 6 for application level, that is the example. So it is a very important topic for this subject. So let us go for this subject. First of all, let us start the work. What is work and its significance? Meaning of work in mechanics is different and precise than we use in day-to-day life, because in our Gujarati we can say work is a काम, but it is not like that in mechanics. So you will find it's an entire different thing in this topic. So what is work? The definition is that whenever a force acts on a body, work is said to be done if the body undergoes a displacement in the direction of force or component of the displacement is in the direction of force. So work done is F multiplied by D. So F is the force and D is the displacement. We can define the work more precisely. Work is equal to force multiplied by displacement component in the direction of the force. So work is equal to F cross D cos theta, and in the terms of vector we can say work is vector F dot vector D. So you can find in very clearly from this figure the force is applied as the angle degree, theta degree here. So component in the direction is F cos theta and displacement is D. Unit of work is Newton meter or joule. If 1 meter displacement of a body takes place in the direction of force under the action of 1 Newton force, 1 joule work is done. So let us understand on a tabletop. If suppose force is applied here and this undergoes the displacement 1 meter, force is equal to 1 Newton. So total work done is equal to 1 Newton meter. So that is 1 joule. Work is a scalar quantity. So things will be clear by watching this video, which is downloaded from YouTube.
Force. Here you can see a boy pushing a toy car. Let the car move through a distance s in the direction of the applied force F. Then the work done due to the application of the force is W is equal to modulus of F into modulus of S. That is, W is equal to Fs. Now let us calculate the work done by the force when the boy is pulling the toy car as shown here. Here the car does not move in the direction of the applied force. That is, the force and displacement are inclined to each other. In such cases, the product of the displacement and the component of the force in the direction of the displacement give the work done. Now resolve the force F. The component of the force in the direction of displacement is F cos theta, where theta is the angle of inclination between the force and the displacement. That is, work done can be written as a scalar product of the component of the force in the direction of the force and the displacement. W is equal to F into S, that is equal to Fs cos theta. A weight on his head and walking horizontally does no work against the force of gravity. Guess why?
It will be clear with examples in the work. Let us see one example. First of all, example is on a railway platform, pulley pushes a trolley weighing 1000 Newton to a distance of 50 meters. Find work done in the following case. There are two cases. First, he applies a 300 Newton force in horizontal direction, and second case is he applies a 300 Newton force at angle 30 degree with horizontal. So let us see the solution. First case is he applies 300 Newton with horizontal. So work done is F into S. So this moves for the distance 50 meters. So here F is equal to 300 Newton and S is 50 Newton. So you can see the total work done is 300 multiplied by 50. So total 15,000 Newton meter. So we can say 1 Newton meter is equal to 1 joule. So 15,000 joule work done is reported. Let us see the second case. He applies a 300 Newton force at angle 30 degree with horizontal. Here he applies force with 30 degree. So as we have discussed, on displacement is in this direction. So horizontal component of this force is causes the displacement. So we have to consider only horizontal component of this force. So work done is equal to F cos theta multiplied by S. Work done is equal to horizontal component force multiplied by distance. So in this case, F cos 30 degree multiplied by S. So 300 cos 30 multiplied by 50. So it is 12,990.38 Newton meter. So we can say it is 12,990.38 joule. Work done by a constant force. It can be represented by graph. You can see that graph can be done with force versus displacement. As we are discussing the constant force, so it remains constant throughout the displacement. So we can find out the work done by area under this graph. So it is F into S. You can see the PowerPoint. It is F into S. So it is clear. I hope it is clear to you. What happens if work done by a variable force? What is the variable force? Because there are so many cases in which the force is 0 or somewhat less, and gradually it is increasing up to a maximum limit. So how can we find out the work done? So you can see the graph. Force versus displacement. So suppose initially the graph force is equal to 0 and it reaches up to maximum F, and displacement is in this direction. So what is the work done? So it is nothing but area of this graph. So that is area is equal to 1/2 F into S. So work done is equal to 1/2 F into S. You can see very clearly in this slide. Now let us discuss work done on a spring. So in this case there are two cases. If suppose spring is there, we can compress it or we can stretch it. So in both cases work done is reported. Suppose initially F is equal to 0 and it reaches to F in both cases. So what is the work done? As you know, the stiffness of the spring is nothing but F upon delta. You can see the slide. It is F upon delta L. So here work done is equal to nothing but average force multiplied by displacement. So what is average force? First of all, force is equal to 0 plus F divided by 2, and it is displacement is equal to delta L. So it is 1/2 force into delta L. But we know that force is equal to nothing but stiffness multiplied by delta L. So we can replace F by K delta L. So it is 1/2 K delta L into delta L. So it is 1/2 K delta L square. So work done on a spring is nothing but 1/2 K delta L square. So you can see the slide. It can be also proved by graphical method. Initially force is 0 and it increases up to F, and as we have discussed in variable forces, it is exactly the same cases. Displacement is delta L and this is the force. So force is reaches from 0 to F. So work done is area under this graph. So that is area of triangle 1/2 F into delta. So F is nothing but K into delta L. So we replace the F here with K delta L. It is 1/2 K delta L square. So work done on a spring is nothing but 1/2 K delta L square, where K is the stiffness of the spring and delta is the stretch length of the springs, or if it is a compression, then reduced length of the spring. Now another case, what is the work done against the gravity? If suppose weight is lifted from one place to another place having the height is equal to h distance. So work done against the gravity is nothing but mgh, the weight of the body multiplied by height. So if we lift the body up to a distance height h, height is equal to h, so total work done is said to be mgh. M is the mass of the body, g is the gravitational acceleration, and h is equal to height up to which body is lifted. So up till now we have discussed three cases. First case, work done by constant force, that is F into S. Second case, work done by variable force, that is 1/2 F into S. And third, work done against gravity, that is mgh. So I think all three cases are clear to you. Now let us discuss the special cases of work done. Suppose man pushes this box, but displacement is 0. So what is the work done? Force is in this direction, displacement is 0. So F dot D, Fd cos theta, D is equal to 0. So work done is 0. So we can say that even though we are applying the force, but displacement is 0, so there is no work done. Let us discuss second case. We are pushing this trolley with the force. Force is in this direction and displacement of the trolley is also in same direction. So what is work done? Work done is equal to F into D in the direction of the force. Now another example, suppose force is in this direction and displacement is in this direction. It happens, suppose friction force is in this direction and displacement is in this direction. So what will happen? Theta is equal to 180 degree and it is cos 180 degree is equal to minus 1. So work done is minus F into D. Work is done against the force, so it is negative. Here it is one interesting case. Suppose a person is having a weight in his hand and he is moving in this direction D. Force is in this direction and displacement is in this direction. So work done against the gravity is 0. please listen carefully. Work done against the gravity is 0. No work done. So we can say that if force and displacement are in the same direction, work is done on a body and it is positive. If the force and displacement are in opposite direction, work is done by the body and it is negative. So let us discuss one example. Calculate the work done in the pulling a block of wood weighing a 5 kilonewton for a length of 10 meter on a smooth plane inclined at angle of 40 degree with horizontal. So let us understand the problem first. Here it is the inclined plane 30 degree. The block is here. We are stretching this block from here to here. It is the S. Weight of the box is W or F here. So you can see in the example the angle here is 45 degree. Angle is 45 degree. The component of the 5 kilonewton weight in the parallel to plane phi is equal to phi sin 45. How it comes? Suppose this is the vertical component, this is the angle theta, and this is the component of the force is parallel to this plane, that is phi sin 45 degree. That is the phi sin 45 degree. S is equal to here 10 meter. S is equal to 10 meter. So work done is equal to nothing but F into S, and that is phi sin 45 multiplied by 10. So that is 35.4 kilonewton meter. So as we can say, it is a kilonewton meter, so total work done is 35.4 kilojoule. Let us take the similar example. Calculate the work done pulling of the block of wood weighing the 5 kilonewton for the length of 10 meter on a smooth plane inclined at angle 60 degree with the horizontal. Here angle is 60 degree. In the previous case it was 45 degree. So let us see what happens. So we are pulling the block 5 kilonewton up to 10 meter here. Here is the weight, and component of the weight in the direction of the slope is equal to phi sin 60 degree. Phi sin 60 degree. So what is the work done is equal to phi sin 60 degree into 10. work done is equal to F into S. So that is 43.3 kilonewton meter. So that is 43.3 kilojoule. So now one interesting comparison is there. If suppose slope is 45 degree, the same wooden block was there and work done was 35.4 kilojoule, and similarly same wooden block was pulled for the 60 degree slope, so work done is 43.3 kilojoule. So we also experience, if the steeper is the slope, we require more work done. So let us recall what we have discussed so far in this work, power and energy. Work done is equal to nothing but F into S. F is equal to force and S is equal to nothing but displacement in the direction of force. As the unit of F is Newton and unit of S is equal to meter, so unit of work done is nothing but Newton and Newton into meter. So 1 Newton meter is nothing but 1 joule. And also we have discussed examples on a work done. We have discussed some interesting cases on a work done. So it will be clear with more example in a next lecture. Thank you very much.